Hello friends, welcome to the second part of the video lecture on merge sort analysis. In this video lecture, we'll be continuously concentrating on mostly the time complexity in the merge sort function. Okay, and we'll also understand the space complexity in merge sort function. Okay, so let's get started. So in the previous video, you might have seen that we had covered uh, the time and complexity of the space complexity of the merge function. Okay, so we had gone with this function, that is the merge function. Then we had seen how the merge operation happens. Then we had seen how the L and the R array, okay, they are combined over time. Okay, so we need to understand how this how this element came into one single form. Okay, like one, how did they got broken up into one elements? Okay, so let's understand how the calling of the merge function happen, merge sort function happens, and how this things gets broken into one elements. Now, so this is the merge sort function. Now here we have the A, P, and R. P is the starting index of the array. The R is the ending index of the array, and this is how we start. Okay, so this is the Q thing that we get the midpoint of that particular array, and how do we get it? That is P plus R divided by two, and we take the lower bound of it. Then we call the merge sort function again recursively. So this is the recursive call, and in this we send the first part of the array, okay, from P till Q till the midpoint. And again, we'll see that I'll call the merge sort function. I set the other part of the array, the second part, that is Q plus 1 to R. Understanding? And then I call the merge function. So obviously, when this recursive function is called and I go inside the first merge sort, again, I'll have to start from the top. So again, it will be checked in that this P and Q which is there. So when I call this function, okay, this is how it will look. So let's understand the working. So this is the merge sort function, and these are the indexes of my array. So I'm having six elements. So let's start. I know the array starts with zero, but for now, for the understanding purpose, let's say that we start with the first element and we go to the sixth element. So this is P and this is R. Okay. So now we got to find out Q. So what will be Q for 1, comma 6? It will be 1 plus 6 divided by 2, which is 3.5. But we take the lower bound of it. So Q is 3. So as Q is 3, we need to call the first merge sort function. So you see that we'll call the first merge function, so some function with this P comma Q, that is P is 1 and Q is 3. So you can see again merge sort function 1 comma 3 is called, right? Now, as soon as this is called, again it will lead to the calling of the other merge sort function because P is less than R. In this case, 3 is R, P is 1. So P is less than R. Again, I have to calculate the value of Q. So what will be the value of Q? It will be 1 plus 3, that is 4 divided by 2. Okay, so the Q value is 2. So again, you can see I call another merge sort function that is again P comma R. Okay, so you can see over here that we get the value of Q, we call this function again, and then Q becomes R again. So in this case, my 2 is again R. So again, P is less than Q. So I take the, sorry, P and R. P is less than R. So this is 1 plus 2 divided by 2. So that is 1.5. The lower bound of it is 1. So again, we get the value of Q as 1. So I call the merge sort function again and I send P and Q. So P and Q is what? 1 comma 1. Okay. Similarly, I call the second merge sort function. Okay, and I get 2 comma 2. So and finally the merge function is called. So in this case, you can see I couldn't have proceeded further, right? Because it's P is not less than R. That's the reason why I ended over here. And that's when we went to the second merge sort function. So in this, when I'm not able to go inside this merge sort function again, I go and check out the second merge sort function. And when I am not able to ahead anymore, okay, I'm coming to this merge function, right? So down this merge function, what is going to happen? I'm going to, so this might be what single elements, 1 comma 1, this is one element. Okay. Then this is another single element, 2 comma 2. And finally, I'm going to just merge this one element. Okay. So this is the level that we are coming to. That means we are breaking down till the single element. So this is what is this particular diagram. So you can see it has been broken down till the single elements. And finally, the merge function is going to combine these two first. That is 12 and 8. We get 8 comma 12. Okay. So now you can see again as this work is done, we go back. The calling goes back to this merge sort function. Now this merge sort function, the work is done, right? So as this work is done, I go back to the second one. Okay. Now in this, obviously this is 3 comma 3, which is a single element. So I can't proceed anymore ahead. Okay. And then finally we come back to the merge function. So now this merge sort function, what had it returned to us? Okay. It had returned to us 8 comma 12. right? And finally, in this MS3, 3, we have one single element. So two elements over here, one element over here, which will be merged in this particular function. So you can see that is happening over here. 8, 2, 12, and 6 is getting merged. We get 6, 8, and 2 using the merge function. Now, similarly, we can say that we proceed ahead. This entire work is done over here, and then we proceed to this particular merge sort function, and a similar operation happens that we call it calls the second merge sort function. It again in internally recursively it calls the other merge sort function. Finally, when I reach this stage, this is what single elements, and then again finally merge it into array. So you can see it is happening here. Okay, we have 1 and 10, which is getting sorted. And then finally, again, 1 and 10 with 2, it's getting sorted, right? And the final merge function will be called over here, right? Over here. When 1, comma 3, comma 6. So you can see, okay, 1, comma, this is 1, 3 till 6. Okay, so all of this entire, this to L array and R array, they are getting merged and get the final array, which is the sorted. Okay. So now let's understand what is the time complexity and what is the space complexity of this object. Okay. So to understand the time complexity, let's move to this diagram. So you can see we have 8 elements at the start, right? Now this 8 elements, okay, are broken down into set of 4 and 4, right? So at this level, the amount of work done, amount of work done is on all the 8 elements, right? Then we break it down. Okay. So here we have n by 2 elements and we have here n by 2 elements, right? So you can see n by 2 plus n by 2. Again, the amount of work is done what? N by 2 plus n by 2, which is n, which is equal to 8. Then finally, again, we break it down more. N by 2 gets converted into n by 4. This n by 2 also becomes n by 4. So similarly, we see we get 4 n by 4. So it is n by 4 plus n by 4 plus n by 4 plus n by 4, which is equal to n, which is equal to 8. So again, amount of work done is on 8 elements. And finally, at the last level as well, okay, we have n by 8 stage, right? So we add up all these things, and again, that comes up to n, which is 8 elements. So you see the amount of work done at each level is on all n elements. Are you getting it? So now we know the amount of work done at each level. So if we find out the number of levels, then we should be able to understand that the amount of work done would be amount of work done at each level multiplied by the number of levels. That would give us the total amount of work done. That would be your time complexity, amount of time taken to do the work. Now, so you can understand this n equal to 8 could also be written as 2 raised to 0 into n raised to 2 raised to 0, right? So 2 raised to 0 is 1, again this 2 raised to 0 is 1, so n equal to n. Again over here, we can see that this n by 2 which is there, right? N by 2. So you can see it is n by 2 plus n by 2, which is 2 times n by 2, right? It is 2 times n by 2. So it can be written as 2 raised to 1 divided by n by 2 raised to. Now in this case, you can see this is 4 times n by 4. That could be written as 4 into uh, n by 4. But 4 could be represented as 2 raised to 2. And again, n by 4 could be represented as n by 2 raised to 2. Now, again, similarly, you can see this is 8 times n by 8. Now, 8 times n by 8 could be represented as 8 can be represented as 2 raised to 3, and n by 8 also can be represented as n by 2 raised to 3. So you can see now, so if we don't know till what level to go, in this we know that we have these single elements, it can't go further. But you might be having huge arrays, right? And you might not know till where to go. So in that case, you might be thinking that there's total k levels, right? K levels. But you know that it has to end. Okay, the height of the tree is not something which is infinite. It has to end somewhere when you'll have a stage when you have all one elements at the leaf nodes, right? So what would be that stage? Okay, so let that stage be something 2 raised to k, right? So this is the zeroth level. You can see this is the first level, this is the second level, this is the third level. Okay, and here my value of k is equivalent to 3 because at this level I get all the values as 1, leave node as 1, 11. Right? So if we, even if we don't know the levels, okay, we keep breaking down. We can say that at 2 raised to k, okay, at kth level, I'll have 1 elements. Now, what will be 2 raised to k? Okay, 2 raised to k is what? You can see it will be the number of elements, right? 2 raised to k will be the number of elements. Now, it is n divided by 2 raised to k. Now, in this case, we can clearly see n is equivalent to 8, right? We have 8 elements, n is equal to 8. And you can see 2 raised to 3 is also 8. So in this case, n divided by 2 raised to 3 will give me what? 2 raised to 3 becomes 8. N is also 8. So 8 divided by 8 is equivalent to 1. Right? So this thing, if I solve in the bracket, I get it just as 1. And finally, if I see what is n equivalent to, n is equivalent to 2 raised to 3, which is 8, right? So if I'm talking about the kth level, at the kth level, obviously, we'll be having one element. So at kth level, it would be somewhere that my 2 raised to k, okay, is equivalent to n. Like in this case, 2 raised to 3, okay, is equal to n. So as soon as 2 raised to k becomes equal to n, this terms becomes value becomes 1, right? So that's the reason why, okay, we normally equate n equal to 2 raised to 3, okay, 2 raised to 3 or 2 raised to k. Now, so when I do that, we take log on both sides, and that's the reason why we get the k thing as k equal to log of n. So that the height of my tree is what? K equal to log n. Now you need to understand that in this case, we have, as we can clearly see, the number of levels are what? One, first level, second level, and third level. Okay, but we can't just talk in terms of number. Okay, we need to talk in terms of n. So we can clearly see in this case that my height of the tree is dependent on the n with the help of log. So we can say the height of the tree is log of n. Are you getting it? So this is how we get the height of the tree. So amount of work done at each level is n, and the height of the tree is log n. So finally, we multiply both, and we get the time complexity of the merge function as n into log n, right? Now let's talk about space complexity. To understand space complexity, we'll just move a bit. So you can see the calling of the function. I've written the numbers. So first this is called, second this is called, third this is called, fourth this is called, and again after fourth is done, fifth this is called, sixth this is called. When sixth is done, finally I go back to the original parent calling, which is three. Okay, and this is completely done. So three is not called again. I just go here. Okay, but three is done, two is done. I come to seven. Seven is called, right? Then eighth is called. After eighth is called, I see that all of this is done. I come to ninth is called. Then 10, 11, 12, 13, right? Then 14, 15, and 16. So this is the sequence of calling. So let's understand the amount of space needed in this case. So to understand that, let's come over here. Okay. So in this case, you can see when the first function is called, we can say the first function will take some space, right? So first is called, then second is called, right? Then third is called, then fourth is called, right? Now, after fourth is called, okay, what happens? The fourth is called and it is solved, so it is no more needed. So after that, fifth is called, right? So we can say fourth is called and we can strike it off. Okay, we can just strike it off. Then we can call fifth in the same place. Fifth is called, right? Then fifth is also striked off, right? Now, fifth is also striked off because fifth is also processed. Then sixth is called, right? So when sixth is called, is sixth called in the same place? Yes. Okay. So sixth is called. Okay. And even sixth is processed. So let it be striked off. Okay. As sixth is done, again we go back to three. Okay. So three is finally completed over here. So we can even strike off three, right? And then so three is striked off. At three striked off, where do we move? Right? We move to 2. Okay, but 2 is not done. 2 is not done because in 2 we have other functions to be called as well. Right? So what do we do? We call 7. Okay, as 7 is called, 7 is also done. Right? Because you can clearly see 7 is done over here. As 7 is done, okay, we call 8. Okay, in the same place. Even 8 is done. Okay, then finally after 8 we have 2 which is done because everything under 2 is called off, right? So as 2 is called off now again, where do I proceed? Okay, I proceed to 9. So 9 is called in like 2. Sure. As 9 is called, after 9 what do I get called? I get called by 10. Okay, after 10 what is called? 11. Okay, so you can see all four places occupied. After 11th is done, okay, so now after 11th is called, you can see that the 11th finishes over here. There's nowhere to go after 11th. So now after 11th, 12th will be called in the same place. So we strike off 11, we call 12, and even 12th is striked out.
So now the 12th is striked off. Now we can see as the 12th is processed, we go to 13. So what we could do is like we can put 13 over here, and obviously as 13 is done, it is processed and it is striked off. So then we come to the next level, right? So as 13 is done, we come back to 10. So that means under 10, everything was processed, so we can strike off 10 then, right? So we strike off 10. After we strike out 10, we come to the next level, that is 9. So we check whether 9 is completely processed. No, we still have what 15, 14 and 15 to go. So where will 14 go? Okay, so 10 is processed, we can put 14 over here. Okay, as 14 is called, 14 is processed right away. Right, so we can just strike it off. As 14 is done, we can call 15, and 15 is also processed right away. So we can call off that as well. As 15 is processed, there's nothing left on the 9 to be processed, so even 9 gets processed, so that is done. Okay, and we can now see that as 9 is processed, we come back to uh, 16. Okay, so 16 can be processed over here, and as 16 is done, we just strike it off. Finally, under 1, everything is done, and so we strike off 1 as well. Okay, so that's how we go about it. So you can see there were 16 calls totally inside the algorithm. And for this calls, you can see that I could just use only this four spaces. Okay, so I'm not talking about the amount of space each cell takes, but I'm saying the number of spaces that is needed is how much. So can we relate this to the level of the tree, okay, the height of the tree. So yes, we can do that. Okay, so we can see that we have level 1, level 2, level 3, this is level 0, right? So we have kind of three levels. Okay, so can we say that even the space occupied is in terms of log n? So yes, it is. Okay, so even the space complexity needed for only the merge sort function, that is also log n. Okay, and obviously we have proved the time complexity to be log n. So we can clearly state that the space complexity is log n and time complexity is log n for the merge sort function. Now we clearly know that for the merge function, the time complexity is n. For the merge sort function, the time complexity is log n. So the total time complexity would be what? N log n. So time complexity for the entire merge sort is what? N log n, wherein for space complexity, we see that the amount of space needed for the merge function is n, okay, and the amount of space needed for the merge sort function is log n, right? So obviously it's going to be n plus log n, right? The space complexity is going to be n plus log n, but obviously, so n plus log n, so we can clearly say that the space complexity for entire merge sort is n plus log n. So that is it. Thank you so much. I hope you have enjoyed the lecture on merge sort analysis. And if you have liked the lecture, kindly like, share, and subscribe. And happy learning. Enjoy algorithms. Thank you.